All right, welcome back. Friday, weekend ahead of us. Halloween on Monday. I don't know how many of you are having parties over the weekend. Maybe a whole weekend of parties. I don't know. Anyway, today I just want to remind you about the mastery exam and how to practice. We're going to take a look. Today there's really no new content. So we're just going to go over three examples. There's three homework problems. You might see that connection. And it's just on sketching the graph from what we talked about yesterday or Wednesday. Okay, so we're going to apply those. The thing is, when you do the homework, all you have to do is put in like I think it's a 1 when you graph it. It doesn't actually check your sketch of it. So this is more for your own benefit. We're not going to assess you on how well you can sketch a graph, but again, the ability to do so will help you to visualize when you see a function what its derivative might look like, what the second derivative might look like at certain areas. Okay? So again, let's see, where are we? We've got the mastery test, preparation resources. So this is in module 5B. And I'm just going to highlight the activities, hopefully, if it opens up. So there's the math shower. Again, that's if you need a little bit of practice or maybe some videos on doing the product rule, the chain rule, the different types. So there's a lot of resources in there and some videos. This one here is a mastery test, and I think it's one of the best ways to practice because it's online and it's really set up. It's times you, so it gets you to the time length of the test. So try to get you done before that, and it's also really looks like the mastery test. There's a function to take a derivative of, and there's 4 choices, 4 answers to choose from. That's what the test will look like, although it'll be on paper. Okay. There'll be 20 of these questions, and I haven't gone all the way through this, so I'm assuming there's at least 20 in there, maybe exactly 20, probably. And you can go through. When you click on an answer, there's instant feedback, whether it's right or wrong. And it does subtract for each wrong answer. The test will not subtract for wrong answers. So this is just a, again, this is just here for your practice. Again, you could just kind of go through and say, until you got the correct, okay, now why is this correct to practice? So it's got a lot of different ones in here, and so I think it's be a good way to prepare. And then for those that want, there's this paper version, which is just, it gives you a function, you take its derivative, and then you can go down to the last page, and it's got the answers of what the derivative is. The one thing is, though, you might, again, remember, sometimes we can put them in different forms, so your form might look different than the one that's chosen. Yes?
How many questions is that?
20 is the actual test. There's 20 functions, so 20 derivatives. So it's about 5% per derivative, per question, right, 20. And again, we'll do that on Wednesday. Monday, we will do a review. So my suggestion is that over the weekend, do as much practice. Any ones that you struggle with, let me know either in advance or that day, and that's what we'll work on and try to get methods for doing it. So that's kind of what we'll be doing. I sent out a message, an announcement in Canvas earlier where I suggested you might want to print this out or at least have it. So this is instead of a PowerPoint today, we're going to take a look at let's make it a little bit bigger. I just use a Word document. We're given a function, and we're going to try to find a bunch of details about that function that will help us graph it. And then once we've got all those details, we've got a place to kind of sketch the graph, and this is exactly coming from the homework. Okay, so the 3 problems. I'm assuming yours will be similar, if not exactly the same. Maybe they're not exactly the same, but they should probably look very similar to this. So as we do this, you'll basically be finishing up the homework. And we're also practicing a bit for the mastery test because we're taking derivatives, right? So one of the things they're going to ask, notice I came up with this chart. I don't know if we'll see how it works. But we'll find critical numbers. Hopefully there's not more than 3 because that's all I put in there. We'll take derivatives on the left and the right. We'll see the value of the derivatives on the left and the right. We will find the second derivative. We'll try to figure out whether it's a minimum, maximum inflection point. We'll try to figure out its concavity from all this stuff. And then that is the information that we're supposed to have that will allow us to do a fairly accurate graph. The other thing I just was thinking, it might also be helpful to have x-intercepts and y-intercepts. So those weren't asked for in the homework, but we might put a few of those in that might help us along. And then again, at the very end, we can always go to Desmos and actually graph it and see what it's like. But for this activity, it's actually best if you try to do it without graphing first, because again, it gets you in there. It'll help you understand it. But again, if you're getting frustrated, a little bit of frustration is okay, but too much frustration, we don't want you going overboard on it. So we could always graph it and then take a look backwards. Okay, so we're given this function with a natural log. Let me, let's go with blue. And we're told that x is greater than 0, and that's the domain because you can't put 0 or negatives into a logarithm. So let's start off with how do we find critical numbers? Get the first derivative and then send it equal to 0. So we're going to need the first derivative right out of the chute. So we'll take the derivative of x. So 7x, its derivative is 7. Derivative of 2 natural log of x. We've got the minus. The 2 is a constant. And the derivative of natural log of x is 1 over x. We okay with that? Okay, so that's its first derivative. While we're in the mood, I don't know if we're in the mood or not, but why don't we go ahead and take the second derivative, because that's something we're going to need as well. And when I work things, if I'm taking derivatives, let's just keep taking them. So we take the second derivative, so we come back to the first one. Let me do it in red, I guess. What's the derivative of 7? 0. And then the derivative of 2 over x, what you want to think of this is now as minus 2x to the minus 1. It just makes it easier to bring the exponent down and subtract 1 without messing up. Because otherwise I mess these ones up all the time. So negative times a negative becomes positive 2. And then when you subtract 1 from the exponent, it becomes x to the minus 2. Right? We subtract 1. So let's just go to short change or make a shortcut. We'll just put that over x squared, right? X to the negative 2 just is in the denominator. So that's the second derivative. Anyway, we could go for a third, a fourth, and fifth, but this is all we need for for drawing the graph. And let me let's see if I can give myself a little bit more room here. This is the other reason why I use Word, so that I can move it around. You can download this, and if you want to, you can use it for, some practice. Someone was showing me this is how they were taught, was sort of you get the critical points and you look to the left, you look to the right, whether they're positive or not. So hopefully this is kind of helpful. So then we said with the first derivative, to find those critical points, we set it equal to 0, and we find the x value that makes that happen. So we've got a single, sort of a linear x. I guess we could subtract 7 from both sides. So we get negative 7 equals negative 2 over x. So I should give myself plenty of room. For me, it's just, again, you can do this in different ways. I would multiply both sides by x, maybe minus x, but I'll just do x. So then you get negative 7x equals negative 2, and then we divide both sides by -7. And we get x equals positive 2/7. That seem about right? So that's a critical point. Does it look like there would be any other critical points? We don't have an x squared. It's got to pretty much be it. When you got a linear, it's going to cross pretty much one time. It's not quite linear, but this 1 over x. So I think that would be it that we have to worry about. So we come up here. Our critical number then is 2/7. And what we want to do is we want to look to the left and look to the right. What is the sign of the first derivative? So we could tell whether it's increasing or decreasing. So what's the first derivative? It's up here. So if we plug in 2/7, what would be a number that is smaller than 2/7? Good. You chose the one I would choose too. So try to be easy on yourself. Don't be hard. 0 is over there. So that's definitely the one we want. And then on the other side, we probably want to use 1 because, again, use the easy stuff if we can. So what we do is we want to find, for this one, we want to find f of 0. And so if we put in, there's a problem with f of 0, isn't there? Oh, shoot, can't quite use it because we get undefined. What if we were a little bit, how about -1? Well, actually, the other thing we've got to do is the critical points occur where the derivative equals 0 or where it's undefined. So that's the one I forgot to look at. So we might also think of a critical number where it's undefined is 0. So we kind of got to get in there. It will probably be, I think, well, again, it's not necessarily where there's an asymptote, but it could be. And actually, I think there will be because it's a logarithm, right? But, so let's back it up. So 0 doesn't quite work. How about a number smaller than 2/7, bigger than 0? 1/7? So if we put in f of 1/7, we're going to get 7 minus 2 over 1/7. You flip the 1/7 because it's in the denominator, so you get 7 times 2, which is 14. So this is going to be 7 minus 14, which is, again, we don't have to worry too much about carrying out the calculation. We just need to know what? Positive or negative. Is that going to be, can you see that's going to be negative? Okay, so that's, we go to the left of the critical number, we have a negative. If we go to the right, for that one we'd probably want to plug in f of 1. 1 is bigger than 2/7, and that gives us 7 minus 2 over 1, which is 2. 7's bigger than -2, so that's going to give us a positive. Again, we don't have to actually carry out the calculations. We just want to know positive or negative. So what's happening at this critical number 2/7? We are decreasing coming to it, and then on the other side we're increasing. So if we draw that little picture, here's 2/7. And what we do know is we decrease down to it, and then we increase on the other side. Okay, so this maybe help us with thinking of what the second derivative might be and such. Does that look like a minimum or a maximum? Minimum, right? So it's, yeah, good. And that's one way we could tell, is if we got the critical point, one side is decreasing and the other side's increasing. That's one way to define a minimum. So while we're at it, let's go ahead and circle. What we do is when we take the second derivative, we'll verify that, because the second derivative at that point will give us concavity as well, right? If it's positive, it'll be concave up, which it certainly looks like concave up. So we would expect the second derivative to be positive there. And since that's going to happen, now I've got this little thing to put the second derivative to the left and the right. we only really need, when would we need to find the second derivative sign to the left or right of a critical value, critical number? One time we would need to do that. Is that? Excellent. Inflection point. This is not an inflection point, is it? I mean, at least I don't think it is. Pretty sure it's not. So, yes.
How do you like know if it's an inflection?
We'll let's talk about that when we get there. There's certain things that will happen, and then it's kind of like you'll know because this thing happened. And right now I don't know because we haven't got there. I try not to think too far ahead. But we could see that, yeah, since it's decreasing and then increasing, it's going to be concave up. And if you wanted to, you can plug in 2/7, right? For concavity, we could just plug in this value anywhere to the second derivative. But let's go ahead and put in 2/7. So that's going to be 2 over 2/7 squared. And again, we're just looking, we don't have to calculate it, we just wait, is that going to be positive or negative? It's going to be positive, right? Because you square something, it's going to make it positive. Got a positive 2 on top. As long as we've done everything's right so far, this is just going to be positive. Positive means a smile, concave up. And that's what our picture's looking like. So so I do this is right here, the second derivative is positive at the critical point. And we don't really have to look to the left or right. If the second derivative was 0 at this critical point, that's when we start thinking maybe it's a inflection point. And then that's why we look to the left and right, see if there's a change. And if there's a change in concavity, then yes, it is. If there's not, then we don't know what it is. Okay. Do we have to look at this critical number 0? Because that's a place where it's undefined. But we got to get out of jail free card because it's not in our domain. So it's like we don't care. Yes.
So why would we do F of 1/7 when it's 2/7?
Okay, because I needed to be to the left of 2/7. I needed to be to the left of the critical value. I tried to go to 0, but 0's not in the domain. But it was where it's undefined, so I couldn't go all the way to 0. So I had to go somewhere between 0 and 2/7, and all I could think of is 1/7. You could have gone anywhere else that was just a little bit smaller than 2/7. That's what I thought. I knew 1/7 is smaller than 2/7.
And that's to find another point?
It's to find whether the derivative is positive or negative to the left. And again, the cool thing is we don't have to actually do all the arithmetic. That's where I was getting a little scared. I forgot about that part. I don't want to do math with 1/7, but I don't have to. I just have to know whether the calculations will yield a positive or a negative. And so don't do more work than you need to. Just say, okay, I know that's going to be positive. I don't really care what the value is, just whether it's positive or negative. Okay. So far, we good? Okay. So again, a couple things we know. We know that it's always bigger than x is going to be bigger than 0. That's the domain, so we don't have to worry about any negative x's. We have one critical value, one critical number. We call them critical values, but they call them critical numbers. We've got this positive and negative on each side, so that indicates something like this. And I guess we're kind of ready now. Intervals were increasing. So then these are all the kind of questions the homework will ask. So we know it's increasing wherever the first derivative is positive, right? And so we know that's to the right of 2/7. Okay, so it's the first derivative is positive to the right of 2/7. So let's go with 2/7, comma, to infinity. And the reason we go on to infinity because we didn't get anything else. And we're also using that the logarithm, the natural logarithm is a function that kind of goes up and up real slowly. We do have 7x as part of the function too, but we're probably going to be okay. Where does it decrease? Well, we know that that's where the first derivative is negative, and so that's between 0 and 2/7, and we know that 0 is not included, so we would just put this one as going from 0 to 2/7, decreasing. Where's it concave up? Everywhere, right? Because it's we don't have a change in concavity. We don't have to have a change in concavity, we would need another critical point, right? Because concavity changes when you go from a minimum to a max, or a max to a min. But we only have one, so we could say from 0 to infinity. Okay, and these are, I just took these questions, I took a little poetic justice on them, made them shorter or something, but that's what the homework is going to ask you for, is all this sort of stuff. You just put it in, and where intervals were concave down, we just say none. It's always concave up. Horizontal asymptotes, so for that we want to think horizontal asymptotes, what's going to happen way out at infinity, right? And for that we kind of look at limits. We come back to the original function. What's going to happen as x gets really big? Well, I know 7x is going to get really big. How about the natural log of x? It gets big slowly, but it still gets big, right? Because it's, yeah. Exponentials are like the fastest growing, logarithms are like the slowest going functions that we have, but it will go to infinity. So they're both going, we are subtracting them, so I guess the fact that x will probably get to infinity faster than the natural log of x, and since you're subtracting less, you could say it's not going to be asymptotic. So none of that. But are there going to be any, so we'll say none for that. And this is where I would say don't struggle too much if you're not really sure. You don't have to go all the way back into limits, because remember, mastery test is just taking derivatives. We're not going to do anything about limits. So that's a place where if I got real stuck, I'll graph it, and if I was wrong, okay, the graph showed me this. Maybe it does have a horizontal asymptote, but vertical asymptote, does it make sense that it would be at 0? Because we've got a natural log of x, and also it's telling us that there is no, the domain does not include anything less than 0. So probably x equals 0 is a good candidate for an asymptote. And so we take all of this information. How are we doing? My graph is way down here. And so we could kind of say, okay, we're going to have an asymptote along here. We know we have a critical value at 2/7. So each of these, I kind of went further out. Maybe I should have went in on this one, but this is from here to here is 1, so that would be about a half. 2/7 would be maybe here. So I know I had sort of a minimum, because what's it doing? It's decreasing and then increasing. One thing that might help us is if we actually took the critical value. The homework didn't ask for this, but if we put it in the original function and got the y value, we could actually have that as a point, right? Would that, you think that would be helpful to graph it? I think so. So we get, let's see, what is f of 2/7? And since we've got this 7 here, that's going to make that arithmetic a lot easier. So 7 cancels, so that's going to be 2 minus 2 natural log of 2/7. It's going to be some kind of a decimal. Let's just plug it in. See if this thing is, so 2 times the natural log of 2 divided by 7. Plug that in, and I get negative 2.5 with some other stuff, but that's probably close enough. And so a negative and a negative make it positive. So we're going to get plus, and then, 2.5. I've already multiplied by the 2. So I get 2 plus 2.5, so that's about 4.5 would be our y value. So that's supposed to be our minimum. It'll just help us kind of get some accuracy. So there's one, let's see, wait, that's 10, 2, 4, 6, 8. So these are 2 going up the way I've got them. So that's 2.5 would be about there. And I guess what we'd have is we have something coming down like this, hitting this, and then going up. Because it's, you know, so I've got my concavity, but that should be about what it is. How would we check? Just go to Desmos. Again, maybe we should have started here, but because it will give us the answers real quickly. But again, and maybe we will do this for the other ones, but I want you to kind of go through, because we've only got 3 homework problems. 2 natural log of x. And yeah, it's sort of maybe a little better than, you know, I didn't know how steep it was going to go. I just knew it was going to go up. That's all that's the thing, is we don't know a lot of details. We don't have to. We just got to know the critical points, how's it behaving around there, and just the general behavior. And that's close enough. We came up close enough. And we could even, looks like my point's off though. I got 4.5. Maybe no, I did. I said 4.5. Okay. That was okay. Is that okay? So that's one example. So that's, oops, I don't want that. Okay. So let's go to the next one. It's maybe a little friendlier. No natural logs or anything. No negative exponents. Just a little bit of factoring probably. But again, we'll go through the same process. We want to find critical numbers, so we take its derivative. So the first derivative is going to be 6 times 4 is 24. Subtract 1 from the exponent, x to the 5th. Minus 7, oops, not 7, sorry, got to take the derivative. 7 times 5. 7 times 5 is 35. Subtract 1 from the exponent, x to the 4th. And again, while we're sort of on a roll, why not just go ahead and put in the second derivative? So then we get 5 times 24. 120? Yeah, that sounds good to me. 120, good. Okay, good. And then 4 times 35, negative 140, okay, x to the 3rd. Okay, so we got our first derivative, our second derivative, we're set to go. To find the critical numbers, we want to find where they are, where the first derivative is 0 or undefined, and in this case we don't have to worry about undefined. So we set this equal to 0. While we do that, let's go ahead and factor this so we can get an x to the 4th out. So can we get anything else? I don't think so. So we get an x to the 4th out here. That leaves 24x minus 35. Okay, and so it looks like we'll have 2 critical values, or critical numbers. So we get one so x to the 4th equals 0, and that happens when x equals 0. So there's one critical number. The other one, I might want to move that because I think actually the other one's going to be negative, is when 24x minus 35 equals 0. No, it's going to be okay. It's going to be positive. So I add 35 to both sides. 24x equals 35, and then I divide by 24, so I get x equals 35 over 24 Just cancel that out. And that's a positive number, a little bit bigger than 1, not quite as big as 2. So 35 over 24. I don't know, what's that? That's like 1.4? That's my guess. 1. Whoa, that's pretty good. 1.46. So just so you kind of know where that is at. And then again, what we're going to want to do is find look to the left of the first derivative, at the critical numbers for the first derivative to see if it's positive or negative. So what's a good number to the left of 0? -1. And again, we could do this in our head if we wanted to, because all we got to do is figure out whether it's positive or negative, right? And so we look up here, we've got an odd exponent, so that's going to be negative, right? A big negative number. We've got a -35, but this is a even exponent, so if I plug in -1, it's going to be even, which keeps it negative. So I've got 2 big negative numbers, answer's going to be negative. So if I'm to the left of 0, the first derivative is negative. Is that okay? So I'll kind of write it out what I did. I said f of -1, well, actually derivative at -1. I plugged it in. I knew the first term is going to become negative, second term is going to be negative, and so I'm going to have a negative to the left. We look to the right of 0 and see what happens. So we're going to look at the derivative when x is 1. That's, again, just an easy number. Plug in 1. Well, if we plug in 1 for here, this is going to be positive 24, right? This is still going to be negative, right? Because you got 1s to the 4th is just 1 times -35. So we've got 24 minus 35. That's going to be negative. And no matter what you plug in, well, all the way till the next critical number. It could change at that next critical number, somewhere in between there. So, but just to the right, that's what we want to look. We came, it's actually negative. Did we, right?
Yeah.
I said, okay, I forgot what I was. So we're negative on both sides. What does that mean? It means it's not a minimum and it's not a maximum. It's a good candidate for possibly being an inflection point. So this is another place we'll look at the second derivative too, but it's a good candidate for an inflection point because it's coming down and then still going down. Okay, so we can't say minimum or maximum. I'm not going to call it an inflection point yet because we've got to talk about concavity, but we could maybe get there. So concave up or down, how do we determine whether that critical number is concave up or down? Check the second derivative. So when we plug in, this should be f of x. So when we plug in 0 to the second derivative, what do we get? 0, because we got those two x's. So we get 0. Here's another thing. Well, that doesn't tell us anything about concavity, except possibly that it might be changing concavity and it might be a place where we have an inflection point. So this is a place where, to answer the question about concavity, we've actually got to look at the second derivative to the left and the second derivative to the right. See if we get a change in concavity. So now we look at the second derivative a little bit to the left. Let's go with -1. We plug in -1. Again, this is even. So this is going to become positive, right? So the first term is positive. The second term, if I plug in a negative and I cube a negative, it's going to be negative, right? Negative, negative, negative. And then I multiply by the negative in front of the 140, so a negative times a negative is positive. So I've got two positive numbers adding together. Second derivative is going to be positive when I'm to the left. Okay. What does the second derivative being positive indicate? Concave up. Okay. Maybe not as, but yeah. And then now if we get concave down on the other side, what can that tell us about 0? That's an inflection point. Okay, so if there's a change in concavity. So we look to the right, And again, we go there, we plug in 1, anything else would work, but so I plug in 1, this first term is going to be positive, this second term is going to be negative, and if it's 1, right, because it's 120 minus 140, and 120 minus 140, not what the value is, but is it positive or negative? It's negative. And so actually, any number up to the next critical point would be negative. So we have a change of concavity from concave up to concave down. And I guess I should have, so this point itself is not, but this side here is concave up. I didn't really anticipate this. And this side down here is concave down. So a change of concavity, we can say, dang, that's an inflection point. So we found one. I didn't know how we would find it, but it's kind of like if you go through the process, things will naturally sort of occur. Okay. Now we got to look at the other one because we still have a critical value over here. But the cool thing is between 0 and 3, this other critical point, which is like 1.4, right? The first derivative should still be negative. We've actually already found that. The second derivative, if we're still to the left of it, we could go all the way. We could actually use the same value, the same point, right? We could use 1, positive 1. It's also going to be negative. So the concavity hasn't changed there. Let's see, what else do we know? We don't know whether the second derivative's what's happening there. But what we need to look is we need to look slightly to the right to see do we have a change from decreasing to increasing. Okay, because then that would say maybe we got a decreasing to, we'd have a minimum. Okay, so what's a number a little bit bigger than 35/24? 2. And again, all we need to do is we put it in the first derivative. Again, you can see this kind of a, so we're going to take a look for this one here. I'll come up, actually let's change colors while we're at it. So I'm going to look at the first derivative at 2. If I plug that in, 2 to the 5th is a positive number. Big positive number times 24 is still positive. So I got a big positive number. 2 to the 4th is positive, but I multiply it by negative 35, which is negative. So now I've got to do a little bit of work. Guess I got 24 and 35, but I'm using the value of 2, so maybe I better actually calculate this. Because 2 to the 5th should be big enough that it's still is positive, I think. 35 to the 4th, 2 to the 4th. And you could also do this, actually, you could use the factored form. Let's do that. Because this is, right, if we use the factored form, 2 to the 4th is positive. So that's a positive number. We just got to see if in this places we get positive or negative. 2 times 24 is 48, minus 35 is a positive number. So we'll have a positive times a positive. So don't break out the calculators yet. We can circle that one. We have a change in the first derivative, the sign of the first derivative. We were going negative to positive. We've got a minimum point. Okay. That's one of our definitions of a minimum point. And what we would do is we could look at the concavity of the second derivative at 35/24. So if we put in 35/24, which is a positive number, 1.4. Again, we could just look at the factored form of this, so we could take a x out of all of this, and that leaves us 120x minus 140, and then that's an x to the 3rd out here. So if we plug in a positive number, x to the 3rd is positive. 120 times 1.4, I think is going to be bigger than negative 140. So this inside, and again, you can plug that in, it's not too bad. You'll see that the inside here is also positive. positive times a positive is positive. So what we come up with is at this critical number, second derivative is positive, which means what? Concave up. It means it's a minimum, which also validates decreasing and then increasing. Decreasing on the left, increasing on the right. So again, those all work together. They should all be consistent. When we get inconsistency, it means we screwed up somewhere in our calculations probably, because otherwise it can't happen. So one more thing we might want to put in is get these actual values. So when x is 0, the function value is going to be 0, 0, right? We kind of figured that one out. That's not too bad. At 35/24, so if we put in 1.4, I suppose it would be nice to have that value. Let's just put it in. So let's get the function value at, I'm instead of 35/24, so I can't graph that, so it's going to be about 1.4, 1.46, and for 1.4 raised to the 6th power minus 7 times 1.4 to the 5th power, come up with negative 7.5 approximately. And again, we're just doing this so we can kind of see approximately where things are laying out. And again, we could answer all of these questions. We've kind of gone through there. There is no vertical asymptotes, probably no horizontal asymptotes, because it's going to go off to infinity on each side. We might want to think about, let's see, as x goes to negative infinity, this becomes a big negative number, that goes there. That becomes positive. I think it's going to go down to negative infinity still, because wait, you put in negative, no, that's going to be positive. It's going to go to positive infinity. Also, we know that this is an even power, so overall, an even polynomial will look like that. Okay, somewhat. So let's go ahead, and we know that at 0, 0 we have our inflection point, and then at 1.4 and about negative 7, so that's 8, about there, we have a minimum value. So I would say it's going to come down like this, give us an inflection point, go down like this, and then not a real beautifully looking graph, but I'll bet you it's somewhat accurate overall shape of what we've got. And again, we go to Desmos to take a look at that. Let's see, 4 to the 6th and 7 to the 5th. For x to the 6th minus 7x to the 5th. That wasn't too bad. Okay, so let's get the kind of general overall shape. And again, if you come in here, if you just kind of want to get it done, remember Desmos will, I found a kind of a new way. I was proud of myself. It's not like genius smart, but I don't know why I never thought of this before. I'm going to define g of x to be the function d dx of f of x. And so you could graph the first derivative, and that way you could find the points. And what this allows you to do is you can now get the second derivative by doing d dx of g of x. And I guess, I never thought of doing that. It's pretty... Okay, so you can graph them both. I guess we're running out of time. There's one more, but that's just for the homework. And let's see, what's the last one? last function, come on, is this one. You can see it's going to have a vertical asymptote. It's just a little, you know, but it's a good one to practice doing derivatives with for our upcoming mastery test. Take the first derivative, the second derivative, go through the same process. It's tedious. It's not real exciting. Yeah, don't invite a date over and say, let's do some derivatives, let's sketch some graphs. That's not really a fun party favor game, but it's something that we kind of need to do, and we'll, you know, we'll get there. But that's the third one from the homework. And it just ties back into what we did on Wednesday. Yes?
So even if you know that it's not an X or does that mean that will always be an inflection? Or?
No, it could be something else. It could be an undefined area. It could be, it's not necessary. The only way it'll be an inflection is if there's a change in concavity. If the concavity doesn't change, it could just kind of be a set, you know. And when you get to Calc 2, you start doing 3 dimensions, and you got stuff that's like a saddle point, and because you're in 3 dimensions, and that's where you really got to apply all this stuff.